Let's just understand what's predictive maintenance in the context of smart manufacturing. Right? Whenever you would hear smart manufacturing, there's a huge focus on integration of autonomy, big data for actionable insights. For example, for a factory, typically one might look at key attributes such as what kind of systems they are incorporating, what kind of technologies have been adopted by factories, how the data is flowing between various different components, various different teams, and last but not the least, what's the infrastructure. Let's understand what's the change observed when we have to tag a factory as a smart factory, right? So on the left-hand side, you would see, again, looking at those four key attributes. On the left-hand side is a traditional automation kind of factory where you would see fixed position robots, manipulators. Those are typically programmed, manually programmed. The data is observed, but mostly used for just monitoring the condition of robots. And typically it is stored on historian SCADA. Now, when you see, so this is not the exhaustive list, but this is for representation. Now let's just focus, shift our attention to the right hand side. These are the factories which we can see that they are leading towards smart factories. So typically they would use autonomous systems. You might have heard such terms such as collaborative robots, right? Technology could be AI, deep learning, AR, VR. A very good use case could be automated quality inspection, digital twin, having a digital replica of the physical asset running, let's say, on a centralized unit, and most importantly, these two twins are connected all the time, right? So the data on the talking about connectivity, data is not just used for monitoring condition, but it is also used for intelligent logistics, what we also saw in sterilized case, and also for predictive maintenance. And typically, these companies, smart companies, also adopt cloud. It becomes easy to manage, various different, especially when you have various different locations, right? As well as understand the health of each machine. So, point of saying this was predictive maintenance is one part of smart manufacturing. MathWorks has to offer. I mean, look at other applications such as digital twin, AI, deep learning, autonomous systems. Even if we are not going to talk about it, there is so much you can do with inbuilt solutions from MathWorks tools. Okay, so in today's talk, we'll ask three questions, and we'll try to answer those. First, how can you easily get started with developing algorithms? Second key question, once the algorithms are developed, what are the steps to test those, validate those before we actually deploy it on edge? And the last bit is taking these algorithms on cloud system. So there is also a question to be asked that what really goes on cloud, what really goes on the edge. So we'll try to answer that as well. So let's just revisit the complex looking machine. Just imagine that this machine fails. The machine which have many moving motors. Sometimes these machines just fail without any notice, right? Even if companies carry out preventive maintenance, there is a good chance that these machines might break down. Now, even if one single motor breaks down, like your printer motor in your printer, if there is a paper jam happening, the entire printer stops, right? So similarly here, apart from natural wear and tear, there could be other problems such as loose electric connection, material flowing through machines. So companies have been spending a lot of time. You look here, Siemens, they talked about it this afternoon, but this is a project which they had done for a train between Barcelona and Madrid, and using predictive maintenance, they increased the uptime to 99.9%. Right? You have ABB, Intel, Bosch, and many others. So it doesn't really matter if you are manufacturing equipment or you're an operating a machinery. Predictive maintenance has started opening doors, and we have started seeing business impact. But is it all that easy? Now, first time when I saw this picture, and as Mohit also talked a bit about, it's not just one team, right? Multiple teams, cross-functional teams, they have to operate together. So it all starts with assets. You have edge devices, and then you have these IT OT systems. Sometimes it could be on premise, sometimes could be on public cloud. You have databases, containers, various different streaming platforms. Then you might also have dashboards, which are more important, right? And where you're going to store your data. So it might be a little overwhelming. So let's just simplify it, and let's look at these four challenges which are very common, right? Too many options to start with. Feature extraction. It's not just the AI problem. That's what it says. Um, then integrating algorithms with existing infrastructure. So not every time you are allowed to start from scratch. So reuse of existing infrastructure is very important. Lack of failure data, and last but not the least, hard to get started. Of a subsystem, which is a servo motor, essentially what it is doing is it is doing a repetitive task of pushing the blocks on an assembly line, right? So we have sensor data. We are looking at the error, which is position error, motor current, and motor speed. Now, as Mohit and Srinivas talked about, their end goal is that the operator, which is looking at all these assets, without he understanding what's predictive maintenance, what's manufacturing, he gets an overview or bird's eye that how are my assets doing. And then you also want to deploy part of code on the edge, right? So here we are adding one more challenge, which we commonly observe is sensor data being not available, right? Many of the times, as you carried out preventive maintenance, timely maintenance effectively, there was no failure. So what do? You want your algorithms to predict failures. So that could be another challenge which can be addressed. And I'll be showing you one user story very briefly, which talks about addressing that. Okay. So this is how the dashboard. On one side, you see a summary dashboard where we are looking at 20 different motors. What's the what percentage system, the entire asset, the location is in bad shape, and then you can also pick a particular motor in this case, and then observe what's the remaining useful life as well as anomalies. Right. So this has been built in Kibana. Whenever we are clicking on a particular motor, a trigger is getting generated. So I'll also show you once we develop these predictive maintenance algorithm, how do you incorporate those with dashboards. Three-step agenda. Let's start with developing algorithm. So this is how the simplified workflow would look like. You have, many of you who are from AI background might be thinking predictive maintenance from machine learning lens, but machine learning just plays a part of the workflow. You need to understand machine, the actual asset, as well as data coming from it to extract meaningful indicators. So Dr. Shayani also talked about it this afternoon, that it's machine learning plus X, right? There's so much more. The domain expertise is very important. So I'll be touching on the feature extraction part. I'll also show you without spending too much time on programming, how can you get started in developing algorithms. So there are many apps which we have added to make your task easy. You as a domain expert, without you programming, getting stuck, you can just directly start working, importing data, extracting meaningful condition indicators. So I'll be showing you Diagnostic Feature Designer. This particular app comes with Predictive Maintenance Toolbox. Okay. Now talking about condition indicators, instead of just looking at raw data as is, for example, vibration, you might look at mean of vibration, standard deviation, and see the change for the entire fleet, perhaps. Right. So mean is one of the time-based feature. If you are looking at data coming from rotating equipments, perhaps it might make more sense to also look into frequency domain. So here, power bandwidth, mean frequency, and so on. There is a recommendation sometimes that you might also find value in looking at time frequency domain features such as spectral entropy, spectral kurtosis. Now, if you don't know, don't worry too much about it. There is a very good documentation available. I have added link here, and I'll also show you how diagnostic feature design looks like. So we are going to import all those 200, here in this case 188 files, observations. All the time domain features are available on a drop down. Higher order features can also be selected, and you can also visualize those, right? So what MATLAB is doing is it's going to all the 188 files in this case and extracting mean from every single, so let's say mean or kurtosis from all the features, correct? And then a feature table gets created. You can also visualize features. So here, if a feature is good feature, it will separate our fault codes very easily, right? So you can also visualize the significance of feature. That's the point. Uh, there is also ranking inbuilt. So after I've selected all the features, what really is most important? So here it is, in this case, it is using one-way ANOVA. There are other ranking methods also available. Better the ANOVA value or greater the ANOVA value, better or more significant it is. That's how you look at it. Once you have done this, you can either generate a code. So many of the apps actually offer this particular facility that you do things interactively and generate code towards the end. So in that way, you also achieve automation, right? You will also see respective functions used for these features. So everything is white box. Okay. You can also pass on these features to another tool which is called classification learner. So here we wanted to, our goal was to identify or classify faults. We have passed on these features to a classification learner utility or app. In this case, it is segregating data between what are the predictors, what's the response. People who are aware of machine learning, you know that you need to divide data into training and testing. So again, that can be done interactively here. Once you are inside the app, again you can plot one feature with another and see whether you are seeing any interesting patterns, right? So you can also select features, reduce the features if these are strongly correlated as well. Now, here is a drop down list. Again, if you're a newbie, there's no harm. You can go ahead and select all the machine learning algorithms, and MATLAB will run all these algorithms independently. So again, the question would be, this could be time consuming. So parallel computing also has been added. So without you actually programming a sequential code to program a parallel computing code, it will compare various different algorithms. And here now it is saying that SVM is the most accurate for this set of data. Okay. You can visualize the accuracy. I'll not get into details of hyperparameter tuning or PCA, but those features have also been added. Like I said before, you can very well extract this model, and the algorithm is now ready to be deployed. Anyone has done this or has seen value? Here are two examples. Metro de Madrid, they have developed degradation models using the built-in features. We also see here another customer, IMA from Italy, and they say that just by using 5 features, they were able to get 89% accuracy. So these user stories are also available. They will boost your confidence, and you can learn from their so-called mistakes or learning, right? Their stories. So those are again available on our webpage. Another interesting story from aerospace domain. So Safran, it's a French company. They used Simulink to generate failure data, right? The data which was very difficult to physically get. Sometimes it becomes very difficult to physically damage you. Let's say if it is a gear tooth problem, and you want to see what's the impact if the tooth is broken. Instead of you breaking down, you can see the impact of it using digital twin, right? That's what they had done. So again, a link to that has been added to it. Okay, moving on, which is the crucial part. Let's say you have built an algorithm. Now it makes sense to take signal processing and feature extraction algorithm many cases to an edge device. The reason, two benefits. First benefit is that if you have many edge devices, it does not make sense to send all the data on the centralized repository or cloud. And if you do that, then you'll be spending a lot of money on the bandwidth, data transmission. Second benefit of doing initial level of signal processing is that you can actually achieve results much faster. So companies prefer doing signal processing, feature extraction on the edge. Okay, but again, it depends on what compute you have available on the edge device. Okay, so what are the steps to before you actually deploy? How do you make sure? How do you validate this? So we're going to demonstrate four-stage approach. So we have developed an algorithm which can run on resource constraint edge device. We'll test the algorithm in simulation. We'll verify the performance in real-time testing. This is again very important. And last but not the least, deploy it on actual hardware. Okay. MATLAB, I mean, even if I'm going to show you a use case for PLC, you know, and you might have attended Dr. Ishu's session where he talked about taking deep learning on FPGAs. But there's much more you can do and take your code from high level to target specific devices. Okay. So here is Simulink. If you have not Simulink, this is a block diagram kind of environment. We are representing at the flow pack machine servo motor. On the right left hand side, you see a controller here that there is a plant. Now what we have done is we have taken the code, the classification algorithm, and embedded here. Okay, so this is the actual what you saw in up was the actual so-called digital twin which we use to generate the data, and we're going to test the algorithm. Here we are looking at two faults, one the mechanical fault, another is electrical fault. There are two features we have selected which are most important in this particular case, and we saw that these were giving good results. We are also normalizing that data and then calling the model which has been developed using classification learner app, right? That's about it. So that's what is happening under the mask, and that's the predict function, correct? So two inputs, and what is happening now is that I talked about so far using built-in apps. You can also create your own app which has knobs, gauges, lamps. So here there are two faults, and you can also see the animation, right? So first we made sure that the algorithm is working fine in MATLAB environment, MATLAB Simulink environment. The next part would be, so you see that this is working correctly. Mechanical failure, the light is lit. You can see the orange light. I'll go to the next part, which is taking it to a PLC, right? And see that if the algorithm is working correctly or not there as well. Now, what we have done here, we have converted into C code, and that has been then deployed on PLC. So this orange looking box, what you see here, that's our PLC. We also have another machine here, which is a speed code machine, and that is mimicking the actual asset, right? So we have not yet connected our PLC with the actual asset. So whatever output actual asset will have, the speed code machine is going to give us that, right? And now once it has been deployed on PLC, we want to make sure that the same algorithm is working and giving exact same results. So that's the double check, right? And once we are happy that this is all working fine, then we can go ahead. I can unplug it from the speed code machine and put it directly on my actual asset. So this is how step by step you would make sure things are right. First in computer, then on rapid prototype on hardware, right? Anyone has done this? So Atlas Copco, Belgian company, a very good example of IIoT or smart manufacturing. They have 120,000 machines, each machine having 50 sensors. The data is getting streamed. They're doing condition monitoring. They're using data analytics, also optimizing maintenance schedules and predictive maintenance, right? So I'd highly encourage looking at their there's a talk, 30-minute talk, and they have used both model-based engineering and digital twin for minimizing cost. Okay. That brings me to the last point, which is taking predictive maintenance algorithms on cloud. Now, why does it make sense to take some part of algorithm on cloud? See, the algorithms which could be compute intensive, which might not run or need to run every second, every, let's say, every minute, but perhaps might make more sense to do this periodically, let's say daily or weekly, remaining useful life estimation, right? So those really find good place and can be deployed on cloud. Okay. So what skills are required? Um, Mohit, I can talk a bit about. I mean, he talked about what skills their team had. Here we are looking at three kinds of skills primarily, right? And there could be an overlap. So here we have engineers and data scientists who are actually developing your models. Then we have dashboard builders, and third, system architects who understand cloud part very well, right? So we're going to start. I'm assuming that most of my audience here today are engineers and data scientists. So how do we get started? So what we'll do is using some historical data available on our archive, I'll develop a predictive maintenance algorithm. Once it is developed, a binary will be then given to my system architect, a piece of software which is called MATLAB Production Server. It's a streaming analytics engine which is available and can run directly on Azure. So it will have it has a persistence layer which is constantly storing the states. Then you also have Kafka, which is connected with the end devices, and there is an inbuilt support available from MATLAB production server. So whenever there is data or whatever trigger you have written, automatically algorithm, whenever the data is there or trigger is there excited, you can actually, the algorithm will run, right? Once the algorithm has completed its task, it will give back the results to Apache Kafka, and then it will be stored in a permanent storage such as Elastic. Then it can be consumed by dashboard builder. In this case, we are showing example of Kibana, but it could be any other dashboard as well, right? So let me show you this again with another app. I'm showing here. I'm using here production sort of compiler. The take anomaly is the algorithm which has been written, and now we are going, it has automatically, you see that multiple dependencies have been added. I go ahead, package the tool, so it will create a binary in my same folder. Now my job is to go ahead as a domain engineer. I just have to load this particular application from the front end which gets shipped with MATLAB production server, right? So this is the front end, a dashboard, and I can upload the application which has been generated. So application is nothing but the anomaly detection CTF. That's about it. So point is that if I make changes to this, I'm very sure that end user is using the latest release. Okay, and this is kind of hot deployment. So that's how, we have taken the algorithm on the edge. I'll not be rerunning the dashboard, but you got the I mean, this is an example. You got the idea. Anyone has done this? Well, this is a company based out of Switzerland, GF Machining, and they have built dashboards which are used for condition monitoring and predictive maintenance. Okay, again, link has been updated here. Now, initially, this picture was kind of a dashboard, or workflow was little overwhelming. It was scary, but as we looked into it, this is how the simplified workflow looks like. You have an asset, you have edge device, in this case PLC, enterprise OD system, Azure, and then we have dashboard here, Kibana. Once it is all, let's say the file has run, triggers are getting generated, you can save all the results on Excel CSV, right? Predictive maintenance is very important that all these components are connected and integrated. Okay, so those are the three things what we looked at today. Now, I'm very sure that not everyone is working on servo motors, but there are many reference examples pertinent to gearboxes, batteries, which are available. You can get started with examples, documentation. We also conduct workshops. So if you are interested in that, no, let us know. There is also a Tech Talk series which could help you to get started, and other support apart from tool documentation training. We also have consulting wing. So the team can actually do handholding in the initial phase of your project. So there is a dedicated page on predictive maintenance consulting. If you're interested, we are happy to connect you with them. That brings me to my summary slide. We started with four challenges, and here is one platform which is going to make your task with predictive maintenance easy, right? So you can, as I said, we started with condition indicators. We looked at diagnostic feature designer to extract features, and I also then showed you classification learner app. Then we also talked about when it makes sense to take your algorithm on the edge. So there are coder products available to easily convert that. Today we talked about taking it to a PLC, and then the last point was also to taking it to cloud, right? Safran story talked about possibility of using digital twin, or let's say Simulink Simscape, for generating failure. And then we talked about various different possibilities to get yourself started. So examples, training, consulting.